layer deposition and also to its applications. So what has it done for society so far? What is the technique? What is needed to implement it? And what has it done for society? So atomic layer deposition is a thin film deposition technique from the vapor phase. And there are, of course, several thin film deposition techniques from vapor phase that exist, and maybe the most easy one is something that you have seen happening at home. If you have a kettle of boiling water, then you generate water vapor, and the water vapor tends to condense on a cold surface, on this piece of glass here, for instance, and you could say that you're making, from the vapor phase, you're condensing a water film on your glass. So there are various ways of, from the vapor phase, transferring material and making a coating out of it. This is maybe the most basic one. Probably never thought of it this way, but I'm showing the example because it's very similar to thermal evaporation. If you think of thermal evaporation of aluminum, it's actually very much this process where you have pieces of aluminum. In this case, you need a vacuum chamber because you don't want your evaporated aluminum to oxidize or to react with air that would be present. So you work in a vacuum chamber, you pump down, or you make sure that there's no air left. You have your substrate here, and what you're doing here basically is you're making your kettle of boiling aluminum, which means that you have to go above 660 degrees Celsius, but anyway, you heat this filament, or you heat this mass of aluminum until it melts, and once it's molten, it's basically the kettle, and the aluminum atoms start to vaporize, and whenever they hit either the chamber walls or the substrate, they will condense, and in this way you're making your film from physical vapor deposition, so just evaporation. You could say again that this is maybe a very simple and maybe not so interesting way of making a film. However, it's actually used at large scale in production. So whenever you see potato chips, the back of a potato chip is basically a polymer film. If it would just be a polymer, too much water vapor would be able to go through the polymer, and your chips you will not be able to store them for several months. They would just go bad. So you need to have on the polymer some kind of film that's better at keeping out the water. And what people have come up with in this case is just starting with the polymer film, and these are these molten pots of aluminum, and you just have your polymer film that's drawn above these molten pots of aluminum. The aluminum evaporates, condenses onto your polymer, and you end up with a metallized film. This is a picture of what such a setup can look like. So you have your molten baths of aluminum here, and you can go up to several tens to hundreds of meters per minute of coating polymer. So this is just from the vapor phase coating aluminum, you could say, on a substrate for this particular application. Now in this slide I will get to atomic layer deposition in the, let's say, one of the easiest processes or most well-known processes for atomic layer deposition. We're essentially also depositing aluminum. So a very important question will be, why don't we just stick to this, because this is simple. Okay, I'll get back to that. In the case of atomic layer deposition, we're also depositing aluminum atoms, but we're approaching it from a very different way. We're packaging the aluminum atoms that we want to deposit first in this molecule, which is trimetal aluminum. So we first package them in this molecule. One of the advantages of doing that is that instead of having to go to a source temperature of 660 degrees Celsius of molten aluminum, we can just keep this at the source temperature of basically room temperature, and you already have vapor pressure. So it makes it easier to vaporize the element that you want to. You package the element, and it makes it easier to vaporize the element to basically be able to transport it to the substrate. So you package your atom in this nice molecule, low temperature vaporization. Secondly, the molecule is designed in such a way to very efficiently react with surface sites, in this case OH groups that are present on many surfaces, many metal oxides, many surfaces have these OH groups present. So the molecule is designed to react in a very efficient way. Wherever it finds such a surface group, it will bind to it. But this binding is self-saturating or self-limiting in the sense that once one molecule has been bounded onto this site, you end up in this situation, and then the remaining gas or the remaining vapor can no longer react with these surface groups. So you have basically a self-saturating chemisorption, and you admit the pulse of gas into your reactor. Wherever it finds surface groups, it will bind to it in a monolayer, sub-monolayer fashion. And then the remaining gas can just stay in a chamber and no further reaction happens. That's the basic idea. Now, after this first step, you've been very successful at depositing a single monolayer, or usually a sub-monolayer. But if you're really honest about it, you haven't deposited aluminum, you haven't even deposited aluminum oxide, you have deposited some aluminum atoms with still a lot of ligands. In this case, since you're aiming for an aluminum oxide film, basically junk, contaminants left behind. And therefore, in this step in ALD, you pump away whatever of precursor vapor, or you flush out whatever of precursor vapor that's still in your chamber. You leave your surface in this condition, and you admit in a second step, and therefore it's alternating exposure of the surface to different gases. So this is the alternation 1, step 1. You pump out gas 1, and you admit gas number 2, which is in this case just water vapor. It cleans off all of these remaining metal ligands, or many of them hopefully, and you're left with, in the ideal situation, and of course the real world is never ideal, but in the ideal situation, the idea is that you're left with a single monolayer or sub-monolayer of aluminum oxide. And the nice thing is that if you notice that you actually have regenerated your original surface groups. And this regeneration allows you to do this in a cyclical way over and over again. So it's a cyclical process where, as the name says it, layer by layer, you're building up your film. Now that brings us back to the question, because in all honesty, it's a very nice process, but you will need this starting molecule, you need pulses of gases. It's probably much more complicated than just thermal evaporation. So you might wonder, why bother with this more complicated method? It offers two main advantages. The first main advantage is thickness control, which is really built into the core of the technique. Every time that you go through this cycle, you're sure that you have added a fractional monolayer usually. So it's really the technique of all thin film deposition techniques that offers the most stringent control of layer thickness down to the atomic level. And for some applications, we'll get back to that later, for some applications this is really crucial. The second main advantage is that it allows you for conformal coating. Now what is conformal coating? Well, if you would be evaporating aluminum atoms, then you would have some source here where the aluminum atoms are generated, so your molten bath of aluminum. The aluminum atoms start to fly in vacuum, and typically whenever they hit a cold surface, a room temperature surface, they will just stick. And that results in typical line of sight deposition, which means that your aluminum film will be deposited here on top of your substrate, maybe here, but you will never be able, using thermal evaporation, to deposit something around the corner, which is conformal deposition. In the case of atomic layer deposition, you are able to conformally coat this full object, even the part that's behind the corner, that's not directly visible from the place where the precursor is coming from. And the main reason for that is the self-saturated chemisorption in this first step. So you should imagine that you have OH groups everywhere here, also down here. When you admit this precursor molecule into your reactor, of course, these OH groups will see the precursor molecule first, and this reaction will happen first at this location. But once this reaction has happened, this location has basically become inert. No further reaction will happen here, and your gas has all the time in the world. Also, the molecules are not like aluminum, they don't stick immediately, so you're, at least not on this surface, so your reaction has all the time in the world to just, the gas can go into pores and into small cavities and around corners and whatever, and you can manage to deposit into very complex 3D surfaces. So the main message is, if you're depositing a film onto a standard planar surface and you don't care too much about film thickness and you don't have to deal with 3D aspects of your substrate, there are easier and probably less expensive ways of depositing your coating, However, if you're aiming for thickness control at the atomic scale, and if you are dealing with complex 3D shaped substrates, then ALD is often the only technique that you can use to achieve the coating that you're interested in. This conformality is very often illustrated by substrates in like trench structures or pillar structures or whatever from microelectronics. However, you can also illustrate it in a more straightforward way using something that we are all very familiar with. This is actually a piece of Kleenex tissue, which you know as a handkerchief or from using in the lab, whatever. If you coat this, so I think you're all familiar with, if you have a piece of Kleenex tissue and you try to burn it, that it will just disappear. You will just combust it into CO2 and that's it. So it will just disappear. If you have a piece of Kleenex tissue that's coated with 10 or 20 nanometer aluminum oxide using this ALD process, because it's conformal, you would expect naively, if you have a piece of textile, that it would indeed go in a 3D way around all of the fibers of the textile. And we will show that that's indeed what's happening. So we have our piece of coated Kleenex tissue here. If we try to burn that, this is what happens. So it burns, it forms soot, and then you can keep burning it. And after a couple of minutes of holding it in this flame, you're left with something, an object that is still looking paper-like. It has the texture of the Kleenex tissue, but very clearly it doesn't contain carbon anymore. So you can just keep it in your lighter flame. Many of you will be doing ALD in a couple of weeks from now, so it's easy to reproduce this. If you have an ALD reactor, just put in some Kleenex tissue, put 200 cycles of ALD, and you will be able to do this experiment. We have often done it also for visiting students. And in this case, you really see the ALD film that you have grown. It's only a film that's 200 angstrom thick, but it has been deposited around all of these cellulose fibers, and so the object that you see here is really the film that you have deposited. And when you zoom into it with an electron microscope, you can really see a lot of hollow tubes. So you really had cellulose fibers around which you have grown your aluminum oxide film. By the combustion of the carbon, you have removed the carbon, but the aluminum oxide is still there. And this is actually the object that you have deposited with the ALD. And so it really shows the conformality of very complex 3D shaped substrates, textile, fibrous materials, porous materials. You can go into very narrow features and deposit your material there, and that's really what's unique about ALD. Coating a Kleenex tissue is maybe not the most advanced thing to do, and this is another application or another example where in this case it's not cellulose fibers, but we were coating carbon nanotubes. So this is basically a forest of carbon nanotubes. So every wire that you see here is one individual carbon nanotube. So this is a cross-section of a quite dense forest full of carbon nanotubes. We exposed it to an ALD process, and we managed, this is for one of these carbon nanotubes, the carbon nanotube, and then you can see here a tri-layer coating of titanium, vanadium, and titanium oxide. So there's not many other techniques that would be able to do this. Again, it's not, in this case, not coating Kleenex, but it's coating, let's say, a nano object. And there are not many other techniques that would be able to do this with this level of thickness control and on this level of complex 3D substrate morphology. And so I think it's fair to say, especially given the last example, that what I hope to convince you is that ALD is really a coating technique for anything related to nanomaterials, because nanomaterials are often 3D objects. They are nanowires, they are all kinds of 3D objects. So you need a 3D coating technique to coat them or to functionalize their surface. And secondly, since it's a small object, you will only be interested in depositing a very thin layer, so your thickness control will be crucial. And so that's the main reason when you look at the history of ALD. The first part of the history of ALD is mainly related, and I'll come back to that, to the need for ALD for a specific application in microelectronics. The recent growth in the field of ALD is mainly related to this fact that people are starting to acknowledge more and more, if you have nano-sized or nanostructured objects, so anything related to nanotechnology, and you want to coat it or you want to functionalize the surface, you need a technique that can do 3D, and therefore ALD is quite interesting and relevant. Very briefly, what can you deposit by ALD? A lot, and especially if you're interested, on many of the slides there are unfortunately maybe not that many references, but these are two papers that I would definitely highly recommend reading if you're new to the field. They give an overview. One was written in 2005, the other one in 2013. They give a very nice overview of all ALD processes that have been reported by that time in very nice tables with a lot of references to existing literature. So basically, if you're new to the field, I would definitely encourage you to look up these papers. This table here, you can see a lot of metal oxides, metal nitrides, metal sulfides, and so on. Unfortunately, maybe not that many pure elements. So metals by ALD is very challenging. Metal oxides, metal nitrides, metal sulfides, you could say, by just looking at this table, are apparently maybe a bit more easy. Very briefly, only one slide. HYCOAT is not really about atomic layer deposition, it's about molecular layer deposition. So what is molecular layer deposition? It must be something different. In essence, it's very similar. That's also why I put both schemes here next to each other. It's very similar to ALD. So it's also a cyclical exposure to precursor vapors and in this way building a film. But the end goal in the case of molecular layer deposition is not to build a purely inorganic film. So in the case of ALD, you could say you start with this molecule. It reacts with the surface, you clean off the surface, and you're left with ideally a perfect inorganic material, and if you would still have some carbon inside here, you would call it a contaminant. In the case of molecular layer deposition, you use a very similar approach. You use cyclical exposure to gas phase precursors, but the precursors are designed in such a way, instead of using water here, you use a more complex molecule that's designed in such a way to intentionally leave certain molecular fragments inside the growing film. So in other words, in this case here, you're not growing a purely inorganic film, you're growing something that's a hybrid material. And for instance, in this case, it's called alucone, for the lack of a better name. But so you're basically growing complex hybrid materials as a thin film on a substrate, where you intentionally leave organic material in the case of MLD, while in the case of ALD, you typically aim for removing all of the carbon from your film, and you just want to have an inorganic coating. So, but in essence, if you know about ALD, you know about MLD, and if you have an ALD reactor, in many cases, you can also quite easily start to do MLD processing. So in that sense, they are very similar, but the end goal is different, and in this case, you're forming traditional inorganic materials or coatings. In this case, you're forming maybe more exotic coatings, which also, of course, opens a lot more room for research, and hence this is also will be the focus of this HYCOAT training network that was discussed earlier. So that brings me to the outline. So I've discussed so far very briefly the principle and the main advantages of ALD. Then more quickly, I'll try to go over ALD process characteristics. A couple of tips and tricks, because many of you will be doing ALD in the near future, so just very briefly, a couple of tips and tricks, and then, if time allows, and then also an overview of some of the key applications of ALD that are around at present. So to discuss in a little bit more depth the process characteristics, I will start off by what you could call a definition of ALD. So ALD is a deposition technique that uses a cyclic process of self-limiting chemisorption reactions of gas phase precursors to deposit a film. A lot of words, but we'll go by what's underlined. So it's a deposition technique that uses a cyclic process of gas exposure, which means that you will need to have a device in which you can do this. So you will need to have an ALD reactor. And overall, ALD is not rocket science. You just need to have a place to put your substrate. You need to be able to heat your substrate because you want to control the substrate temperature. And then you need a way to be able to expose this substrate to different pulses of gases. For water vapor, it's very simple. You just have a reservoir with water and you have water vapor for free on top of that. In the case of TMA, you're buying a precursor bottle and also the vapor comes free just above in your precursor bubbler. So the only thing you really need is to have valves that you can open at the right time to introduce the right gas at the right point in your process. So the valves are very important. you need to control your substrate temperature, and you need to control the temperature of these lines and also of the whole process chamber, because you want to avoid condensation of your vapor. So those are all of the critical parts of an ALD reactor, you could say, and for the rest it's not really rocket science. It's a quite forgiving process because of this self-saturating chemisorption reaction. In principle, no matter how much precursor gas that you introduce in the chamber, if this process works well, given enough time, it should saturate the full surface. So you're not really limited with very difficult ways of devising gas flow inside your reactor. You just need, in principle, valves. You admit pulses of gas. You have a heated substrate. You avoid condensation. And very importantly, you also need to have a way to evacuate your gas in between these two pulses. Because if these two vapors meet each other in the gas phase, you will be creating a lot of powder and you will be destroying your reactor. So you need to have an efficient way of, once this vapor has done its job, to evacuate it out of your chamber. And there's two typical ways of doing that. One way is a purge type reactor or a flow type reactor, where you basically have a continuous flow of inert gas. On top of that continuous flow of inert gas, you give the pulses of the gas of interest, of the precursor of interest, and then in between pulses, to avoid the two molecules to meet in the gas phase, you just have enough purge gas. So you try to have a very small volume here, you try to have a nice flow regime, and you're basically flushing out whatever gas that is not needed. So this is a flow type reactor, and there are many different flavors of that flow type reactor. Another way of approaching it is, instead of relying on purging with inert gas, is relying on simply brute force of pumping, and just whenever you don't need the gas anymore, to just pump it out using a vacuum pump, a high vacuum pump. And if you go back to base pressure, to sufficiently low pressure, you can also be sure that the two gases will never meet each other. So this is basically the basic layout of an ALD reactor. So again, it's not rocket science. You need valves, you need some way of evacuating the gas from your chamber, you need heating, and you need heating typically of the whole chamber to avoid condensation. And in particular, the evacuation is done by either purging, so in a flow type reactor, and many of you will be working with this type of reactor. This is actually a picture that I got from the University of Bochum's website, so many of you will be using these types of reactors. And many of you will also be using this. This is a picture of one of the reactors here at Ghent University. So both are, and have their advantages and disadvantages, but anyway, you will learn more about that in later talks also. If we go back to the definition of ALD, so we need a reactor. It's a deposition technique that requires cyclic exposure to gas. So now we have a reactor that can do that. Then the gas cannot be just any gas. It needs, of course, to be a particular gas. It needs to be a precursor. What are the ideal properties of a precursor? Well, first of all, its main purpose is to volatilize the element that you're interested in. So it needs to be very volatile, preferably. It needs to be extremely reactive with the groups of interest, but on the other hand, by itself, it needs to be thermally stable, because you don't want it to spontaneously decompose, because then you will no longer have this self-saturated regime. If it starts to spontaneously decompose, it will just grow in an uncontrolled way. So you don't want this. So you want to have a molecule that's stable by itself, but that's very reactive towards specific surface groups. You want to avoid gas phase reaction. Of course, it shouldn't do anything unwanted with the substrate, and it should be pure. But the volatility, the high specific reactivity, and the thermal stability, you could say, are really the three key properties. So you're really packaging an atom in a designed molecule, and the key design parameters for the molecule is that it should be volatile, it should be stable by itself, and it should be highly reactive to certain groups. So those are basically the three key requirements. Very briefly, there are various types of precursors. I will not go into the details. Later today we'll have a much more detailed and in-depth discussion of ALD precursors. As everything in life, all of these different classes of precursors, they all have their own advantages and disadvantages. Unfortunately, as everything in life, nothing is perfect, and you have to deal with the disadvantages and hope for the advantages. It's actually much more complicated. Again, these are these two recent review papers that I highly recommend. These are just two pictures that I stole or that I copied from from one of these review papers, and you can see that it's actually much more complicated. So there's a huge zoo and variety of different classes of precursor molecules that have been developed for the deposition of ALD coatings. Since many of you will be working with diethyl zinc and trimetal aluminum, there's one thing from a safety point of view that I would like to briefly highlight. Some of these precursors are highly reactive. They have to be highly reactive because they have to very efficiently react with these OH groups of your surface. The fact that they are highly reactive means that some of them are also pyrophoric. This here is a movie of what happens from AkzoNobel. This is diethyl zinc that's just being exposed to air. And this is what happens if you try to extinguish the fire with water. So if you're ever running in the ALD lab with a small bottle of diethyl zinc or trimetal aluminum, have a lot of respect for those molecules because you don't want this to happen inside a building or inside your lab. If ever something happens, definitely don't try to extinguish it with water because you will make it much, much worse than it already was. So just that's also usually at research level conditions, you're working with small amounts. But still, you should be conscious about whenever you're walking around in the lab with a small bottle of diethyl zinc or trimetal aluminum, this is what could potentially happen. Just wanted to draw your attention to that because many of you will be doing ALD. So have respect. I mean, we have been doing it for many years. It is possible to do it in a safe way, but be respectful of the molecule. So on the aspect of precursors, so the packaging of the element, there will be a talk later today in a lot more detail. When it comes to the second gas, which you could call the reactant gas, also there, of course, you have a choice. In most of ALD literature, this reactant gas is usually a relatively simple gas, like water or ammonia or a relatively simple gas. There's a lot of literature on highly reactive gases like ozone, and there's also a lot of literature on using for this second step not a simple gas, but a plasma. So in some way, and if we go back, on this ALD reactor, for instance, you can see there's a plasma source here on top. The reason for having this plasma source is effectively to be able, in this step, to be able to activate whatever gas that you're admitting to create activated radicals. These activated radicals will be highly reactive, and that can be beneficial in the second step for basically cleaning up the surface here. Very briefly, I will only spend one slide on plasma-enhanced ALD just so that you know that it exists. So the potential advantages of plasma-enhanced ALD is that for this second step here, you get to relatively simple combustion chemistry. You don't have to rely on very nice chemical reactions with the remaining ligands on your surface. Whatever is carbon will just be combusted off. So in that sense, it's, let's say, simpler and very aggressive chemistry. Because of the fact that you so efficiently can get rid of carbon, often it can result in better film purity. In the case of ALD, remember, you want to get rid of all of the carbon in your film, so the more reactive cleaning that you're using here, or the more reactive agent that you're using here, the purer your film will be, and it can offer also deposition at lower temperature. Of course, there are also some disadvantages. You can have substrate damage if you're not careful. Typically, the conformality is a bit more limited. Your reactor design becomes a bit more complicated, and it's also maybe a bit more difficult to scale it to batch scale. Anyway, if you're interested, you can read more about this in several excellent review papers on this topic of plasma-enhanced ALD. As the last part of the sentence, so we have seen, okay, we need cyclical exposure of a substrate, so we need a reactor with valves and heating. We need dedicated precursors, which you will learn a lot more about this afternoon. But we also need these self-limiting chemisorption reactions. Very quickly, what are they? Well, if you have adsorption, you can have physisorption, which is quite weak. We don't want that because it's not specific, and you will have multi-layer, layer on top of layer, so you cannot make it specific. So you like to have strong interactions, for instance, an aluminum-oxygen bond, in the case of TMA water. You want to have chemisorption, stronger interaction, specific interaction, and you want to have this in a self-limiting way. So in other words, as has been discussed before, this is your starting situation. You open the valve for the precursor gas to enter your chamber. which means that you start dosing precursor along the x-axis, and the coverage of your substrate is supposed to increase, but up to a certain level. So it's supposed to saturate, that's the self-limiting part, because once you have reached this stage, the idea is that you no longer have reaction and that it's just a saturated condition. What's important here is the sub-monolayer. The name or terminology of ALD is atomic layer deposition, but it would be very naive to assume that every cycle you're depositing a full layer. So every cycle, most often you're depositing a kind of fractional monolayer or a sub-monolayer, because very often on this very simple cartoon, it's drawn as if all of the OH groups can take part in the reaction. Sometimes you're dealing with issues like steric hindrance, where only, for instance, imagine that there would be another OH group in between here. Well, you have all of these ligands here, that OH group will no longer be accessible. So in the most naive picture, every time you're consuming all of your adsorption sites, in reality, it's usually only a fraction, or not everything is accessible. And so therefore, atomic layer deposition, it should have been maybe called atomic sublayer or submonolayer deposition or something. But I mean, the idea is there, but it's not always, or you should keep in mind that it's definitely not always a full monolayer that's being deposited. Now, since this is very difficult to measure, because here you really need surface science, what people typically do in the field of ALD is to characterize ALD growth by something that's called the growth per cycle. And this growth per cycle is actually related to this. So how much precursor can I adsorb on my surface in every cycle, and then that will be the result of the film growth during that cycle. So you can see here that this is as a function of the number of times that you have gone through this ALD cycle. So after 1, 2, 3 cycles, every time you're adding a little bit of film, you can measure this film thickness. Normally this is a nice linear curve, because every cycle you're adding the same amount of material, and the slope to this curve, to this linearity curve, you call the growth per cycle. And this is like the typical measure that you will find in ALD literature for growth rate, the growth rate of your film. It's important to realize that this growth per cycle, although it's referring to kinetics, that it has nothing to do with the chemical reaction process, the chemical reaction kinetics of this process. It just has everything to do with how much material you can deposit in one cycle on your substrate. So it has nothing to do with this reaction as a function of time. It just has something to do with how many molecules can I store on my surface during every cycle, and that will determine my film growth. It's also important to realize that often this can be substrate dependent. And so that means at the start of your growth process, it doesn't always have to be perfectly linear. Your film growth as a function of the number of cycles. You can have substrate enhanced or substrate inhibited growth, because the fact that initially you're growing on whatever substrate that you're putting in your reactor, you start growing aluminum oxide, and after a while you start to grow aluminum oxide, in this case on top of aluminum oxide. So here you're not growing on a substrate, here you're growing the film on existing film. Here you start to grow on whatever substrate that you have put in your reactor. It's easy to understand that this chemistry can be very different from this chemistry. And the packing density of atoms or molecules that you can make here can be very different from the packing density that you have here. So in that sense, it should be linear, but initially you can have changes depending on the initial substrate conditions. On Tuesday, there will be a talk on area selective ALD, where people are very much interested in this type of behavior to end up with selective growth on a particular substrate and not having any growth on the other substrate, which is very often related to this part where you try to aim for inhibition on a certain substrate and you try to have very nice growth on a neighboring spot, but we'll get back to that in a future lecture. As a final slide on this ALD process, your substrate temperature is also very important, and this is like the classical graph to illustrate the effect of substrate temperature on the amount of material, so on the growth rate per cycle, on the GPC of your ALD process. Typically, you have a window where you have real saturated ALD, and then outside of that window, if you go to too low or too high temperatures, things go wrong. and they can go wrong because of 4, in literature, typically mentioned reasons. They can go wrong if you're at too low temperature because you start to have uncontrolled physisorption, and you can start to say, okay, I have a much faster growth, which might look as an advantage, but unfortunately this is not controlled and will not be conformal and so on, so this is not real ALD. Very often if you're at too low temperature, nothing happens anymore because you don't have enough energy to activate the chemical reactions that are needed. On the high end, you can start decomposing your molecules, or you can have thermal evaporation, or just molecules that should be on the surface for the reaction to, or should stay on the surface for the reaction to continue, that are just desorbing. So in those regimes you don't want to be. Typically you want to be in this ALD window where you have nice saturated growth. It's important to note that very often in literature, for the ease of understanding, this is drawn as a nice flat line. It's important to note that this does not need to be flat. There are a lot of very nice and well-behaving ALD processes where the growth rate per cycle within the ALD window is not flat. And to name one of them, TMA water, for instance. So this is the ALD window here, and you can see that the growth rate per cycle is actually decreasing. There can be very good reasons for that. So in general, it's drawn as a flat line. It can be a decreasing line. It can be whatever. The main message is the ALD window is determined by saturated growth conditions. So by having a nice saturation, self-limited reaction, and then the GPC is whatever it is. So this is an example. So many of you will be developing and characterizing ALD processes. Whenever you're trying to get to an ALD paper on a new process, these are typically the graphs that you're aiming for. So you have investigated whatever new chemistry. You confirm that you have nice linear growth as a function of the number of cycles, and from this you determine your GPC, your growth per cycle. And you do this over and over again for different dosing conditions of this precursor. And then the graph should look like this. So it should saturate, your GPC should saturate as a function of the dosing time of this precursor. It should also saturate as a function of the dosing time of this reactant. And then you do these experiments in principle at different substrate temperatures, and in this way you can get your saturated GPC as a function of temperature. So it's basically doing a hell of a lot of these depositions. All of these curves will hopefully look linear. You fit your GPC for different process conditions, time, and temperature, and you process all of that data into these 3 graphs. And for these 2 graphs, typically there can be more than 2 because you can do this at different temperatures. And your ALD window is determined in temperature whenever your saturation graphs look like this. So this is, if you're reporting a new ALD process, this is in principle what you are reporting. If you have a nice ALD window, nice chemistry, then this is what it should look like. And this is what it does look like for the prototypical TMA water process. Maybe more quickly, some tips and tricks if you plan to do ALD in the near future yourself. Whether you're using a home built or commercial reactor, if you want to be sure about the status and the health of your reactor, it's always a very good idea to have TMA attached to it. And if you want to be sure that there are no leaks or no funny things going on with your reactor, you just put in a sample. You give 100 pulses of TMA, but no water. And then in principle, if all goes well, nothing should have grown. If something has grown, it means that you have leaks, it means that you have something funny going on, because if you're only exposing to 100 times this, it should be the equivalent of only exposing it to 1 time of this. So it's not really clear, not really correct to say that nothing should have grown, but the only thing that should have grown is this single monolayer. So you give 100, 200 pulses of TMA. If you don't intentionally introduce water, it's a good sanity check, nothing should have grown. For any reactor, especially also purge type reactors, if your purge gas is not pure, always something will grow, but if you grow too much, you're not really in a good ALD condition because something is wrong with your reactor. Then when you're starting to play around with a new precursor molecule, so you load it into this bubbler, when you attach it to your reactor, the first thing to check is that precursor vapor is actually coming into your reactor. A very efficient way of doing that is just putting your substrate temperature really high, to make sure that whenever molecules would enter, vapor molecules would enter your reactor, for sure they will decompose. So in essence, you're intentionally positioning yourself in this regime. You go to very high temperature and you intentionally aim for whenever precursor molecules will enter your reactor, they should decompose, and you use that as a kind of, because it's very difficult to determine unless you have FTIR, and it's not so easy to determine whether vapor is actually making its way into your reactor. It can be that you don't have enough vapor here, it can be that it's condensing somewhere, I mean, a lot of things can go wrong. So if you want to be sure that the vapor is actually reaching your sample stage, you just put it at really high temperature and you wait for decomposition to happen. And what can you do to enhance vapor reaching that place? Increasing the temperature of these lines, and in particular also increasing the temperature of the bubbler, because typically the higher the temperature, the more vapor you will get. And so that's what's being done here. So you can see here, this is the amount of material that's deposited. This is not ALD, this is just thermal decomposition, CVD, if you want to claim it that way. When your bubbler is at 90 degrees Celsius, nothing is happening. So in other words, at 90 degrees Celsius, there's not enough vapor reaching your substrate. You increase it to 110, then something starts to happen. If you increase your bubbler temperature to 125, then you start to see very clear decomposition. This is not ALD, but this is the first step, you could say, towards ALD, because you have actually verified that something is reaching, some molecules are reaching your heated substrate. Now to go into ALD, you're at much too high substrate temperature, so once you have determined this, you can fix this temperature, because now you know, okay, what to do to get a vapor into your chamber. Now you want to start playing with this temperature, and you start at high temperature where you have the decomposition, and you just reduce your substrate temperature, and at some point you will reach the stage where you don't see decomposition anymore. This is not because the precursor vapor is not entering your chamber, because you didn't change anything here, but this is because your surface temperature has just become too low for the molecules to decompose. So on this graph, you have basically gone from this regime into this regime, and you have determined the upper edge of your ALD window. And from then on, you can start doing experiments from this temperature on. You're sure that your precursor is hitting your substrate, and you can start decreasing temperature and start to do these types of experiments and fully characterize your ALD process. So, but if you would start with a new ALD process, that's really the way to go. First of all, make sure that your reactor is behaving properly by studying a very simple and prototypical ALD process like TMA water, and just pulse the TMA, making sure that you have nothing funny going on with the reactor. Making sure that precursor molecules are actually hitting your substrate. You can do by this kind of in situ decomposition test, but you will very clearly see it also on a substrate whether anything has decomposed. It will look nasty, but you don't care about it. As long as you see decomposition, it's fine. And then reducing the substrate temperature to find the upper edge of the ALD window, and then you can just continue. And check for saturated growth and so on. And then, of course, so characterizing a real ALD process, it can take you a couple of minutes, because it's really doing a lot of experiments, and they all take time and so on. Very quickly, as a last tip, ALD should be conformal in the ideal case, but you should not take this conformality for granted. And I'm showing some images here from our own research from a while ago, but I'm just showing it because for us, at least in the lab, it's a nice way, again, mainly for pump type reactors, I'll come back to that, but it's a very nice and efficient way for testing ALD processes. The trick is basically, you have a piece of silicon, you put a piece of just everyday aluminum foil that you can buy in the supermarket, you fold it in two if you need to, and you just cut a hole in it, and you press a second piece of silicon on top of that. This is making a kind of 3D trench, where you can deposit. This is line of sight deposition. Here, the surface inside this trench cannot directly see the source of the gas. So you can, in principle, check for deposition around the corner by checking for deposition in this region here. And it's very efficient to do that. You don't need an electron microscope, you don't need any fancy equipment. When your deposition is finished, you just disassemble the structure. And if it looks like this, you have a very nice process but it's line of sight, because you're only depositing at the edge, and you should have deposited here as well. So you have done very nice ALD, but it's not conform, and this can happen in some circumstances. While if it's nice ALD, you will have deposited something all the way to the end, and you directly visually see it. You don't need an SEM, you don't need any fancy equipment, you can just check your conformality by looking at whatever you have deposited. So this is also a very easy trick. Unfortunately, and if you're interested, we could elaborate over during the break or something, but unfortunately it only really works for these pump type reactors. If you're working on a flow type reactor, it's still possible to use this approach, but you need to have, instead of the household aluminum foil, you need to have more complex structures that are being produced, for instance, by VTT. They're called pillar hole structures. There are also other options that you probably have. But these are also very easy structures with a similar methodology, where afterwards, after the deposition, if the deposition is conformal, it should have been around the corner. And afterwards, you can very easily rip off the top and visually verify whether deposition has been possible around the corner. So for testing conformality, it's really useful, and often for ALD processes, it's important, especially for instance for plasma-enhanced ALD processes, it's important to verify conformality, because it's not because you're growing in an ALD process, and it's not because you think that you're doing ALD that de facto it will be conformal. It really makes sense to verify. Okay, that brings us here. For the last part of the talk, hopefully around 15-20 minutes, I would like to focus on some of the applications of ALD very quickly, but where has it made an impact on our life and where has it made an impact on society? And as mentioned before, the main advantages of ALD, you will want to use it if you're aiming for very accurate thickness control and if you're depositing onto very complex shaped surfaces. Unfortunately, it also has limitations. The atom that you're depositing needs to be packaged in this molecule. And after the deposition, you don't see any remnants of this molecule if all has gone well in your deposited film. So you have this step in energy and in cost and in complexity in having to make this molecule. And afterwards, during your process, your whole goal is to completely and utterly destroy this very nice molecule. So by its very nature, that will mean that there will be a certain cost and effort involved in making this, while it's not really present in the end product. So the atom needs to be packaged. The second disadvantage is that it's very nice to grow layer by layer, but then in reality, there's a lot of atoms in a bulk piece of material, and in reality, if you translate this into real-world growth speeds, that this can be a very slow process. And to illustrate just how slow it is, actually, I should give credit to Fred Rosenboom, who at an AVS ALD conference at some point showed, I think it was a picture of his beard, and was starting to compare the growth rate of ALD films to the growth of his beard. I saw that presentation and I started to think, okay, when you have the growth of your beard, but you also have other like natural processes that are perceived to be slow. So you have the growth of your hair, the growth of your fingernails, the growth of your toenails. These are typical rates expressed in, let's say, human units. If you translate that into angstrom per second, as we are sitting here, our hair is growing 5 nanometers per second. And as we are sitting here, our nails are growing by about 1 nanometer per second, and our toenails are apparently growing by about half a nanometer per second. For many ALD processes, you're growing, especially in a research type reactor, you're growing maybe 1 angstrom per minute, or per half a minute, or per 5 seconds, whatever, but I mean, you're not reaching these rates. So in other words, as you are standing next to your ALD reactor, these things are growing faster than your film. Okay? Then you can go to the growth of trees. These are sequoia trees. They are thickening by about 1 centimeter per year. That translates into 4 angstrom per second. So the trees outside of your lab are typically growing faster than your film. It gets worse. You can look at geological things. The US is drifting apart geologically from Europe because of continental tectonic plate shifting. That's about 2 centimeters per year. So as you are standing in Europe next to your ALD reactor, your reactor is shifting away from the US faster than your film is growing, unfortunately. You can even look at the tidal effects that are causing an increase of the radius of orbit of the moon. That's about 4 centimeters per year. So as you are standing next to your ALD reactor, the moon is moving away from you at 1 nanometer per second, while your film is growing maybe 10 times slow. So when I mean slow, it's really slow. The only thing in nature that I could find that's similar in growth rate is the growth of these objects in caves, stalactites, stalagmites. Those are growing even slower than ALD, but these are also only growing at really geological time scale. So you might wonder when you look at this, and of course you have to be careful when showing this at conferences, because very quickly people walk out of the audience after having seen this slide. If they would have seen it thinking, okay, this is a completely academic and irrelevant technique, we will never be able to do anything useful with this because it's just too damn slow. That's not true. So ALD is definitely not some obscure academic curiosity, and I'm just using economic numbers here. This is from a market research company with the growth rate in the field of atomic layer deposition equipment, existing size, and then the forecast. And we're ending here with $8 billion of total sales of only reactors. Then you have precursor companies, you have companies making bubblers, you have companies making all kinds of peripheral equipment. So the total ALD market, it's not some obscure academic curiosity, it's really used in industry, and I will show you the couple of domains where it is used. Mainly in microelectronics, but I will also show some examples of other applications in the next slides. And I think it's fair to say that since 2007, I mean, many of you have laptops here. If ALD would not have been invented, or if ALD would not have existed, since 2007, the advances in microelectronics would have stopped. So other advances that have been made in processors and cell phones and so on, a lot of them are really related to the fact that ALD is available and can deposit in a very controlled way these very thin layers. Unfortunately, it's usually relatively slow, but I'm sure also that with spatial ALD, later on in this presentation or in this later on today, spatial ALD can be quicker. But overall, I think it's fair to say that unfortunately ALD, you need a molecule, and by its very nature, you're depositing layer by layer, atomic layer by atomic layer. So overall, unfortunately, it's typically relatively slow, but it has made really its mark on society, especially in the field of microelectronics and potentially now also in other fields. So to give you a small overview of the applications, I will try to discuss very quickly 3 main applications where the breakthrough has happened already and where there's really mass volume production and dedicated reactor designs and so on to make these applications work. And then I will finish off with a couple of what I believe are potentially emerging applications where there's not real products, at least as far as I know, on the market yet, but where you can see a lot of potential and hopefully breakthroughs in the coming years. So the first 3 current applications, the first real breakthrough application, if you don't mention electroluminescent displays, but like large scale breakthrough application of ALD has been in microelectronics for processors and memories. When you think of scaling, I think we're all familiar with the fact that microelectronic circuits have become smaller and smaller, and Moore's law and so on. I will not go into detail, but so transistors in general become smaller and smaller, down to the level, and we should remember this is the size of an influenza virus. So they're really making in microelectronics things at really the nanoscale, so really small scale where you need to deposit layers that are only 1 or 2 nanometers in thickness, so you need to have very accurate control. And the way microelectronics works is that every year or every 2 years you want to scale, so a transistor that is now this size, you want to scale it to half the size and half the size and so on, so you just have like this scaling law where every couple of months or years you want to decrease the overall size of your transistor. And the point is, at some point, that if you decrease the width of your transistor, for it to still function, for a long time you also had to decrease the thickness of this critical gate oxide layer. So this is your source, drain, gate, This gate oxide is like the insulator that is preventing leakage current from going in this direction. So all of your current should go in your transistor in this direction. You don't want to have leakage, but you want to have electrostatic control, so you need to have some oxide here that's preventing leakage, but that's enabling electrostatic coupling of whatever voltage that you apply here to have its effect on your semiconducting channel underneath. So this gate oxide is really at the very heart of your transistor. For a very long time, people were scaling this gate oxide thickness, and so this is the thickness of this gate oxide. So initially it was maybe several tens of nanometer, then at some point it was 10 nanometer, and people kept scaling, and then you were reaching the year 2000 and 2002, and at some point people were only left with 1.2 nanometers of SiO2, which is just a couple of monolayers. Now the disadvantage is, if you start to do leakage current measurements across such a structure, that you have something that's called quantum tunneling, and quantum tunneling, from the moment that your barrier becomes too thin, even though you still have a pinhole-free barrier, it just becomes transparent to electrons. And you can see here, this is the oxide thickness, and then the tunneling current, and you can see for an oxide thickness of 3.5 or 3.2 nanometer, there's not a lot of issue, but once you start to get to 2 nanometers or 1.5 or 1 nanometer, you start to end up with thousands of amps per square centimeter leakage current, which meant that this was simply not useful. You couldn't scale further. So microelectronics industry was facing a situation where they wanted to keep scaling the width, which meant that in principle they would have had to scale the thickness as well, but they ran into a hard barrier, not being able to scale the thickness any further because of this parasitic effect. So you couldn't scale it anymore, so that meant basically that microelectronics would have stopped. It didn't stop. Why? Because people realized, okay, I have this equation. This is something that you want to scale. This is something that all of a sudden has become a constant because you cannot scale it further. But there's a third parameter in the equation that you can also play with. This third parameter is the dielectric constant of your oxide. For SiO2, this is around 4. If you decrease this, you can leverage that by increasing this. Unfortunately, that means that you can no longer use SiO2, you need to switch to another material. And that other material needs to be deposited with excellent uniformity on a large scale and with excellent thickness control. Because given these numbers, and this is a field where 1.2 and 1.5 nanometers for these engineers is a world of difference. So you really need to have excellent thickness control, perfect uniformity across a large surface area, and that's where ALD came in. So in the early 90s, and you may remember the graph of ALD publications, people started to realize, okay, by the year 2000, this will be a problem. So people saw this roadblock coming up. They started to investigate this. There were some proof of concepts, and then in the year 2007, the first real large-scale production of an alternative gate oxide replacing SiO2. And so basically, enabling further scaling of this while not having to worry about this problem by being able to increase this while decreasing this. So this was the real first breakthrough application. So high K needs to be deposited, you need to control the layer thickness, and you had no other real solution for doing it. So this was one of the first breakthrough applications in microelectronics. Of course, there are also many applications in memory materials, but I mean that would take us too far. Another key application that's more recent in microelectronics is double patterning or multiple patterning. If you think about microelectronics, you're trying to define these type of structures, 34, 53 nanometers and so on, but up to today people are actually using light with a wavelength of 193 nanometers. So in principle, standard optics will tell you that your Rayleigh criterion does not allow you in principle to print sub-wavelength features. So you need to come up with some solution to be able to use this wavelength of light in order to print such small features. People have come up with many tricks, but one of those tricks in recent years is more and more involving ALD. And this schematic is very simplified, so it's not even fully correct, but in a very simplified way, what people are doing is you use lithography to define the location of the things that you want to print. you use ALD and the thickness control of ALD to very accurately determine these dimensions. Then you do a little bit of etching and you're left with your ALD grown structures. You remove this part and you're left with the pattern that you're interested in. It's oversimplified, but it just means that you use lithography to basically more or less define the overall location of the feature, but you use deposition and growth to really define the critical dimensions. And so the critical dimensions of during your lithography is really being performed nowadays not by, you could say, not by lithography, but by deposition and the thickness control during deposition. So this has been a big breakthrough application in recent years. So you have this annual growth rate of 30% that's being predicted, and that's also already being realized in recent years, is mainly related to, you have high-K applications for processors and for memory, and in recent years you have a lot of applications in this patterning, and as devices continue to shrink and to continue to become more and more 3D, people are expecting more and more applications of ALD to emerge in the field of microelectronics. Because all of these very thin layers, they really need atomic level control. And as you can see, many of these structures are 3D. So using other deposition techniques, you have a very hard time imagining to ever be able to deposit inside these very high aspect ratio structures. So I think this market research agency is probably very correct. When you look at these trends, from now on people will need to use more and more ALD for being able to produce these structures. A third application that's also quite recent and that also has really started to emerge in real industrial use, I'll go very quickly, is surface passivation of solar cells. So these are two different types of solar cells. In principle, as light comes in this region here, you generate your electron hole pairs. And then the idea is that you capture your electron hole pairs in your contacts before they disappear because of recombination with certain defects in your substrate or at the interface. Now you don't just have to worry about defects in the bulk of your semiconductor, you also have to worry about defects at interfaces and at surfaces, and that generates surface recombination. And it has been found out, or it has been demonstrated, that if you deposit, for instance, for this type of solar cell, a thin aluminum oxide layer by atomic layer deposition, that you can enhance the lifetime of the carriers that you are making in your solar cell, that you can enhance them from, for this example, 166 microseconds to 307. So this means that this solar cell, the carriers will survive longer, they will have more chance to be captured by the contacts, and in other words, this solar cell will be more efficient than this one. The trick is that you use the aluminum oxide ALD coating to, in essence, avoid surface defects at this interface to play a role in the survival of the carriers that you're generating there. If you want to know more, there's a very nice review on this by Dingemans. So if you want to know more, please read this review. It has become in industrial use, and of course for solar cell production you have to make a lot, so their throughput was a key issue. You have applications where you can think of having batch reactors for coating several thousands of wafers per hour. Something, and I will not go into detail because I'm sure that Paul Poot this afternoon will be talking a lot more about the spatial ALD, but another variant of ALD that has become very important in this field is something that's called spatial ALD, and it's basically doing ALD on a hockey table. So on a hockey table you have this air bearing effect where you can just push things almost effortlessly over a gas bearing. If you imagine that gas bearing not just being inert gas, but at the same time also injecting your reactive gases as you are pushing your substrate through this reactor. When the front of your substrate is hitting this, you have the first part of your ALD cycle, then it's progressing in the other spatial part, and you have your second exposure, while the other part of your wafer is receiving this exposure. And so if you make this long enough, by just pushing a wafer through this type of setup, if it's long enough, you can have the equivalent of 100 ALD cycles by just pushing a wafer through a setup that's a couple of meters long. And so this is definitely enabling high throughput production. These are the types of equipment, so this is really industrial level. These are the types of equipment that people have been building for this, and I'm sure this afternoon that there will be a lot more details on this and on these types of spatial concepts. So of course, there are other applications also, but I think as a kind of general overview, that it's fair to say that application in microelectronics, so mainly the HYCOAT and in processors and in memories, the lithography application and the surface passivation of solar cells are probably at this moment the most large-scale applications of ALD. Then there are also a couple of, you could say, emerging applications that maybe not have yet made it to real commercial products, but where people have really spent a lot of time and effort in demonstrating that there's a lot of potential for ALD in these fields. One field is encapsulation. So similar to the potato chip bags, if you have something that's very moisture sensitive and you want to encapsulate it, you need to have a good moisture barrier. This is the thickness of the film that you can apply as a moisture barrier. So ranging from a couple of nanometers up to 100 micron in this case. Typical polymer films have hundreds of microns of thickness. And then this is the water vapor transmission rate, so the amounts of gram of water that is transported per square meter of coating per day. So you can imagine if you're transporting a couple of grams of water per day into a chip bag, that the chips will go bad. Just as an illustration. So this is really the amount of water that's being transported through the package as a function of the film thickness of your package. If you're using polymers, you're more or less stuck in this part of the graph. So polymers are unfortunately, by their very nature, not very good barriers. Then you have all kinds of inorganic films that are deposited by plasma-enhanced CVD or by thermal evaporation or by sputter deposition, so all kinds of inorganic films that are typically situated here and that are traditional, you could say, inorganic barrier coatings. People have started doing already many years ago also transmission tests for ALD coatings, and this here is a brief summary of some of the results that have been reported. Of course, these are very difficult things to characterize and to test, and very long measurements. But anyway, these are the numbers that you can find in some papers that have been reported for ALD coatings, and you can see that the very nice conformal nature and the pinhole-free nature of ALD enables much better, you could say, inorganic barrier coatings. So for much thinner films, you already have a much better barrier than for many other techniques for depositing inorganic coatings. And this has inspired people to look into the use of ALD coatings for instance, coating OLED displays or coating very moisture-sensitive materials. As far as I know, and maybe some people in the audience know, I guess a couple of people in this audience know a lot more about this than I do, but as far as I know, at this moment, this is not yet in full production, and I'm looking to one of the people in the audience who is more or less nodding, but anyway. So you could say that this is maybe on the verge of a breakthrough where large companies, you can see here, this is an announcement from Vico from a couple of years ago, where large companies are perceiving a potential market opportunity for really starting to do this at a large scale production. Most likely this did not make it, as far as I heard from other announcements on the internet more recently, but I'm sure that some companies are really looking into this for making OLED displays for cell phones and so on, because these OLEDs really need extremely good water vapor barriers to protect them. Maybe I'll skip this in the interest of time. So encapsulation for lighting applications and display applications, encapsulation of moisture-sensitive materials for lighting applications, I definitely consider as a potential emerging application. Another application that has also been studied already for a couple of years is trying to use ALD for enhancing battery materials. This would mean coating powders. This would also mean, so this is far from microelectronics displays, this is coating battery powders like lithium cobalt oxide powder. This here is if you charge and discharge lithium cobalt oxide in a quite aggressive way, you end up with this curve as a function of the number of times that you have cycled the battery of your laptop. These were quite harsh conditions as far as I was told, but anyway, the trend is there, and I think we're all familiar with that trend. If you have just bought a laptop, your batteries last for a certain number of hours. And as your battery grows older and has been cycled, charge and discharge more, typically that decreases. Now, people have found out that if you just give a couple of cycles of ALD, and this should not be nanometer-sized coverage, because if you're depositing 1 or 2 or 3 nanometers, it becomes too much around your lithium cobalt oxide, and you're just preventing lithium from going in. So if the layer is too thick, you're just killing your battery, which is definitely not a good idea. But if it's like this magic layer of a couple of angstroms, it preferably grows probably at locations that are otherwise very prone to degradation. And this causes this kind of passivation effect where your battery can apparently be cycled many, many more times than for the unprotected material. People are looking into it for trying to scale this up, and this is just one example of a company, Forge Nano. There are many other companies, ALD Nano Solution and a couple of other companies also looking into this, so this is just one example to avoid confusion, but people are looking into this for trying to coat tons of material. So there is already, this is a picture of an existing setup, but there are also plans for upscaling this even further, for coating battery materials with a very thin protective coating, hoping to advance the lifetime of your battery. Whether it will make it or whether it will not make it, but at least it's been demonstrated that in principle it works. The rest will be economics, whether it makes it or not. A last field of applications, which I'm personally very strongly believing in potential application, and maybe there are already a lot of applications there that people in academia just don't know about, because I can imagine that also companies value secrecy in whatever production techniques that they are using. So maybe there is already a lot of things going on that we simply don't know about. But looking at it from the academic point of view, there's definitely a lot of potential added value, even if you have a relatively expensive coating and a relatively thin coating. But if you can enhance something in the field of medical applications, I'm sure that people will be willing to pay for that. And so just from that economic point of view, personally, I see a lot of potential for medical applications. Not that we are strongly working on that on this point. I mean, there is some activity in the group, but it's just some examples, some preliminary examples. This is again this Kleenex tissue. If you coat the Kleenex tissue with 200 cycles of aluminum oxide, we could make the Kleenex tissue that's normally designed to do this, we could make it hydrophobic. So if you can play with hydrophilic versus hydrophobic, it's something that can be of relevance for biosensing and so on. And again, it's a very simple experiment. So besides, if you coat some Kleenex tissue, you can very easily demonstrate this to visitors in your lab, and by putting the Kleenex tissue in a lighter, you can also very easily show the ALD code. So in that sense, it's a nice gimmick for having lying around in your lab. The second example is, for instance, antibacterial coating. It's not all ALD coating, so this is a piece of material that was treated with bacteria and then put in a breeding environment to let the bacteria multiply. So you can see that just the material non-treated is of course not antibacterial, the bacteria just grow on top of it. If you deposit aluminum oxide, it's also a good host for bacteria, they just keep growing. But if you are depositing certain other materials, they stop bacterial growth. So just another example, it's a relatively simple and straightforward example, but if you think of biomedical applications, I'm sure that there are a lot more ideas that are much more advanced that have a lot of potential here, and that's also explaining the fact that at the University of Oslo, mainly within the HYCOAT program, people will be focusing on biomedical applications of MLD, ALD type approaches for this field of applications. As a last point that I would like to discuss, need for dedicated reactor designs. An ALD process always looks like this. An ALD reactor may look very different. All of these pictures are pictures of ALD reactors. These are designed to be put in a clean room. These are designed to coat many objects. These are designed for roll-to-roll applications. These are designed for coating the backside of these solar cells. So ALD reactors can look very different, and the reactor design really needs to be optimized for the application at hand. So if you have a good application in mind, first of all, you need the chemistry. You need to show that the chemistry works, and this is what has been done, for instance, for the batteries here. At small scale, you need to show that the chemistry works, and then you need to think about upscaling, and typically upscaling means that you need a new reactor concept. Because you will not be able to use a reactor that was optimized for microelectronic applications to coat battery materials. So every time that you have a new application, typically, if you really want to go to large-scale production, you will need to upscale it, and there's a lot of need for engineering ideas on reactor design and how to ensure that the gas can efficiently interact with your surface. That's what it boils down to in the most cost and time-effective way. So that brings me to the conclusion. So I hope that I have convinced you that, or that I have been able to demonstrate that this is the principle of ALD. So you're depositing a thin, usually inorganic film by self-saturating cyclical exposure to two gases and self-saturating reactions during those exposures. I hope that I have been able to demonstrate that it's been a key enabling technology, especially in the field of microelectronics, and nowadays also more and more in the field of photovoltaics, where it really has gone large-scale production, and that there are emerging applications, for instance in batteries, in encapsulations, and also hopefully in the coming years for biomedical applications, and hopefully also in other fields. So it's not some obscure academic technique, it's really something that has already made a huge impact on society, and where as a community I guess we hope to make even more impact on other fields in the coming years. And with that I would like to thank you for your attention. If there are any questions, or it's been a long talk, sorry. But sure.
I will discuss, you explained about conformality, and you said that viscous flow reactor, so the foil is not suitable to check the conformality of viscous flow reactor, so you need to use fluorophores. What is the difference, and does it mean that you shouldn't use viscous flow reactor for coating of the closed pores?
No, it's a very good question. The only thing that I was referring to is that this particular macroscopic structure is only, and of course you can also use it in a viscous flow reactor, but you can only really rely on the data when you're using a pump type reactor. And the reason is, so this is pressure and mean free path of molecules, and this is the mean free path of TMA molecules at a certain condition, just as an example. So you can distinguish between viscous flow and molecular flow. And the point is that for the nanoscopic features, imagine that you want to coat anodized alumina or very porous, nanoporous things. It's important to realize that in a viscous flow reactor, at the reactor level, at the millimeter, centimeter, decimeter level, you're in viscous flow. But inside your nanostructures, you're always in molecular flow. In the case of a pump type reactor, when you look at the mean free path, in your structure you're in molecular flow regime, but also at the millimeter or centimeter level you are still in the molecular flow regime. So this means that you can use structures here that have an entrance of 1 or 2 millimeters and be sure that you are in the same flow regime as you would have in a nanoscopic structure. So in other words, by using millimeter-sized openings at this pressure regime, you're working in the same flow regime, and therefore you can assume that the results will be meaningful and can be scaled to nanoscopic features. In a viscous flow, if you would use this type of structure, you would be in the viscous flow of your reactor regime, but not in the molecular flow regime of your nanoscopic structures. And so therefore, VTT, amongst others, and I think mainly VTT, have come up with this concept of using MEMS-based, so not millimeter, but micrometer-sized structures that are laterally etched. They look very similar to this. The idea is also that after deposition, you just remove the top and you can visually see how far your film has penetrated. But unfortunately, you cannot just make them with household aluminum foil. You need to have a clean room and micrometer-sized manufacturing and etching of this layer and pillars in here and so on. So this is something that you need to buy. This is something that you can just make yourself. And the point is that this of course you can use it in both types of reactors, but if you would use this structure with millimeter-sized gaps in this type of reactor, you're actually more probing at the flow regime of the reactor level than at the flow regime of the feature level, which is actually what you're typically interested in if you want to scale your results to like anodized alumina or trenches or whatever that you typically want to coat. Any other questions? It's 10:30, so maybe it's time for a break. Thanks a lot for your attention, and let's have a coffee instead.